We're going to have a look at z-scores now, and what we use them for is to measure the distance of each observation from the mean in standard deviations. So when we are calculating z-scores for each of our observations, the values that the formula produce are called standardized values. Standardized values are very useful for comparing data values. These values have no units, so no matter what units the data was collected in, once the values are standardized, the units do not count anymore. The values produced are on the same scale, and this is why we can use these values for comparisons. Standardized values are also useful to identify outliers in our data. So we have a lot of information here on z-scores, so I'll explain each point separately so we can understand what's going on. We'll take a look at the formula to calculate the z-scores now. So the formula that we'll see in books looks like this, which reads as z equals x minus mu divided by sigma. So I'll just go through the formula to explain some of the new symbols we have here. The x we have is just the observation that we want to standardize. The symbol we have here is called mu, and what this represents is our population mean. This would be appropriate to use if we surveyed everybody in the population. Surveying everybody in the entire population is not always practical. What we do is take a sample of our population and survey them. We use x bar to denote the sample mean. What x bar is giving us is an estimate of the true population mean mu. It's just important to note the difference behind the meaning of the two symbols. If we remember from summary statistics, the mean is the average value of our data using x bar equals the sum of xi from 1 to n all divided by n. So the third symbol we have in our formula is sigma, and this denotes the population standard deviation. Again, this would be suitable to use if we had surveyed everybody and found the standard deviation of our data. When we've only surveyed a sample of the population, we use S to denote the standard deviation of the sample. So again, S is giving us an estimate of the true population standard deviation, as it will be difficult to survey everyone. So the standard deviation is measuring the spread of the data around the mean, and we find the standard deviation for our sample using S equals the sum from I equals 1 to n of xi minus x bar all to be squared divided by n minus 1, and then we square root our answer. So when we are dealing with a sample of people from our whole population, we alter our z-score formula to read as x minus the sample mean divided by the sample standard deviation. One of the first points we made about z-scores was that the values they produce are called standardized values. In essence, what this means is that the data goes from being normally distributed with mean mu and variance sigma squared to being normally distributed with mean 0 and variance 1. So we have some more new notation here, so I'll just explain what all this means. The n here is shorthand for normally distributed data. What this means is if our data is normally distributed, a histogram of the data should be bell-shaped. This here is just shorthand to denote normally distributed data, where n is for normal, bracket mu, which is our population mean, and sigma squared represents our population variance. We know from before that the variance is just the standard deviation squared. So when we've calculated the z-scores of our sample, the variance will now have mean 0 and variance 1. If our data is normally distributed with mean 0 and variance 1, then we call this the standard normal distribution. So what I've done here is I've taken 100 recorded observations from a study and I've generated a histogram of them. We can see that the bars of the histogram are roughly bell-shaped. This is an indication to us that the data are normally distributed with a mean of 49.1 and a variance of 8.271. Now we're looking at an example where we have recorded maths exams for 10 individuals.